Okay. The Raman spectrometer instrumentation techniques we discuss here. So, infrared microwave spectroscopy discuss the instrumentation laser source, sample, then detector. Basic instrumentation for Raman spectrometer is laser source, then sample cell, wavelength selector, radiation transducer, then computer data system. A block diagram. അപ്പോൾ അതിൻ്റെ കൂടെ നിങ്ങളോട് ഞാൻ ഈ വീഡിയോ നിങ്ങൾ വാച്ച് ചെയ്യാം. ഓക്കെ ഈ വീഡിയോ നമ്മൾ ടെക്സ്റ്റ് ബുക്കിലേക്ക് പോകാം.
So, what is a Raman spectrometer? Well, Raman spectrometer is simply an instrument that measures this Raman effect to identify a chemical or molecule. There are a range of different measurement techniques used today. Arguably the most common is Backscatter Raman, shown here. Laser light is fired at a sample and the photons are measured from the same side from which the laser light entered. A technique which has gained popularity in recent years is spatially offset Raman. Here, photons are allowed to travel through the sample and the Raman photons are measured from a different point. This technique is very powerful as it allows you to see through transparent or translucent containers. This has been employed, for example, at airport security. Another common method is transmission Raman. In transmission Raman, the laser light is fired from one side and the Raman photons are measured from the opposite side of the sample, after the photons have travelled through the sample. This gives you a complete bulk measurement of the sample, making it ideal for quality assurance applications. However, this technique requires quite high attenuate spectrometers to measure. Another method is surface enhanced Raman. This method is very popular within academic institutions. Here, gold or silver particles are deposited and the sample measured across them. This gives a greatly enhanced Raman signal, allowing for the individual molecules to be probed. However, it has thus far been limited in industrial applications because of the need to deposit these particles. There are a number of other methods for measuring Raman signals. These include time-resolved Raman, resonant Raman, standoff Raman, and confocal Raman, and many more do exist. So what does a Raman spectrum look like? Well, here we have the Raman spectra from a paracetamol tablet, and as you can see, it's very complex, corresponding to the complex nature of the molecule. As already mentioned, every molecule returns its own unique Raman response. Ramans are typically measured at lower energy to the input light, Stokes, but they can be emitted with higher energy, anti-Stokes. The main problem with Raman systems is the scattering process is weak, with cross sections below 10 to the minus 30 centimeters per steradian. This is significantly lower from absorption techniques, for example, and this has limited market take-up. The strength of the Raman tone is directly proportional to the inverse of the input laser light raised to the power 4. Therefore, in principle, using shorter frequencies gives stronger returns. However, other effects occur when you measure, for example, at 532, such as fluorescence, which can contaminate the signal. The shape of the spectra is not a function of the input wavelength, but the properties of the molecule itself, and it is this that can be measured by a Raman spectrometer. The technique has become a viable tool for analysis in recent years as laser technology has matured and dramatically reduced in cost. The Raman process is weak and typically requires relatively high power lasers of greater than 50 milliwatts. So, what is a Raman spectrometer? Well, it is a device that measures the Raman spectra or the Raman response of a given sample, allowing you to identify or measure properties of its nature. Thank you for time to listening. If you wish to...
Okay, അപ്പോൾ നമുക്ക് ഈ വീഡിയോയിൽ പറഞ്ഞ കാര്യങ്ങൾ കൂട്ടിച്ചേർത്തിട്ട് വേണം നിങ്ങൾ ഇതിൻ്റെ നോട്ട് എഴുതാൻ കേട്ടോ. അപ്പോൾ then there is a source and we will have liquid or powder sample. Then the laser is almost ideal as a ramen source. നമ്മൾ സോഴ്സിലേക്ക് പോകുമ്പോൾ source, laser source, sample illumination system, super spectrometer. The sources used in modern Raman spectrometry are nearly always lasers because their high intensity is necessary to produce Raman scattering of sufficient intensity to be measured with a reasonable signal to noise ratio. Because the intensity of Raman scattering varies as the fourth power of the frequency, argon and krypton ion sources that emit in the blue and green region of the spectrum have an advantage over the other sources. Some common laser sources: argon ion wavelength range and krypton ion wavelength range 530.9 or 647.1, helium neon 632.8 nanometer, diode 785 or 830 nanometer, neodymium YAG 1064. The sources are laser sources because of the higher intensity. Then sample illumination system. Liquid samples. A major advantage of sample handling in Raman spectroscopy compared with infrared arises because water is a weak Raman scatter but a strong absorber of infrared radiation. Thus, aqueous solution can be studied by Raman spectroscopy but not by infrared. This advantage is particularly important for biological and inorganic systems and in studies dealing with water pollution problems. Solid samples. Raman spectra of solid samples are often acquired by filling a small cavity with the sample after it has been ground to a fine powder. Polymers can usually be examined directly with no sample pre-treatment. Gas samples. Gas are normally contained in glass tubes 1 to 2 cm in diameter and about 1 mm thick. Gases can also be sealed in small capillary tubes. Then a sample model is defined and drawn here. നിങ്ങൾ ഇതൊന്ന് വായിച്ച് നോക്കട്ടെ. ഹൈലൈറ്റ് ചെയ്ത പോർഷൻ ഇതെല്ലാം കൂടി കമ്പൈൻ ചെയ്തിട്ടാണ് ഇപ്പോൾ പറഞ്ഞിട്ടുള്ള പോയിന്റ്സ് എല്ലാം കൂടി ആ വീഡിയോയിലും ആ സ്ലൈഡിലും കാര്യമുണ്ട്. നിങ്ങളിത് വായിച്ച് നോക്കുക കേട്ടോ.